I've been talking a little bit more generally about the steps involved in training these models, and there are several ways to do it, as with most things. I'll talk about one framework that you can use to develop these models, and that we use, which is detectors. So a little bit about detectors. It is an open source Python package that was developed and is maintained by Meridian. And I think we have the main developers in this project are myself, Oliver, who is here in the room, and Bruno, who is online with us. So I'll have a link to the project a little later on, but I encourage you to explore the documentation that we have there. But yeah, so at a glance, Catus is built on top of many great other open source projects, including SciPy, NumPy, and Librosa that we use a lot for the data processing, the creation of the spectrograms, for example. We use a HDF5 as a database structure. HDF5, for those not familiar with, is a great hierarchical data format widely used in many scientific disciplines. And we use PyTable, which is the Python interface for that. And finally, for the machine learning or the neural network work, we use TensorFlow, which is, again, one of the most used deep learning frameworks today. I would say that and Torch, or its Python version, PyTorch, are probably the two frameworks that most people will use. So everything that we do with Catus is like compatible and leveraged on everything that TensorFlow does, which facilitates the exchange and the use in different applications, as we'll see a little later. So now we talked about that, all those steps involved in creating a deep learning model. And I would like to go through some code that uses Catus to implement those steps. One thing that I would like to say is that, you know, I would be very happy if you use Catus and you find it useful, but I am by no means saying that this is the only way of doing things. There are other great projects out there, and I encourage you to use them. I think I am more interested in seeing people using deep learning for underwater acoustics, and most importantly, sharing their models and what they and their results, observing some or all of those items that I think are good practice. So now we change the screen here a little bit, and unfortunately, due to our technical difficulties, I won't be able to do this as interactively as I was hoping, but I think we'll get most of it anyways. So just bear with me here for a bit. There we go. I'll try to make this a little bigger. Yes, so I was planning to run these as it's called the Jupyter Notebook, which is an interesting, I think, platform for this kind of environment where you have a tutorial or a lecture, something like that, because it allows you to create. It's basically a HTML page, a web page where it's interactive, so you can add text, add code, and run things. What we are seeing here, however, is a frozen version of that, a snapshot of that, because we were having a bit of problems with the AV here, but I think we'll still get most of it, and I will share the notebook itself with the rest of the material. So if you are interested in running the code yourself, you can. Before we start digging into the code, I'd like to say that these will be like what I consider a very minimum version of building one of these models. It is by no means a comprehensive guide. What I'm hoping to provide with this is an insight into how to implement those steps. You see that it's not a whole lot of code. It's not too difficult, but there are lots of things that we won't explore. There are several corners where if you are actually developing a deep learning model to use as a detector, a classifier, in that development cycle that I mentioned, you'll probably spend a lot of time thinking more carefully about some steps that we will just take the default values and glance over here. So with that being said, with this tutorial, we'll go through the steps of creating a binary snapshot neural network for killer whales. So what does that mean? This is a neural network that, when presented with a clip of audio represented as a spectrogram, will tell it if that clip contains or not a killer whale of a vocalization. To start with that, we need to import the modules necessary, and we use here a lot of code from Catus, which provides several functionalities for dealing with the data and creating these models. But this is all happening in Python, so you can leverage everything that the Python ecosystem of libraries has to offer. One example is this library called Pandas, which is used for data manipulation. So the first thing that we'll do, we'll load the annotations that we have. And in this example here, I have a very minimal example where we have 2 recordings on, and we will use one of these recordings for our annotation or for our training and validation set, and the other would be reserved for a test set. But the idea is that the same steps, if you just add more data, you can run exactly the same steps and it will just take the rest of the data for you. So this first step, he simply loads the annotations. And what are the annotations? Annotation is basically a text file or a CSV file, a comma-separated values file, which contains 4 fields. In our case here, it has a start and end time for that vocalization. It has the file name, which tells which file we are talking about here. In our case, that's just one, so it's not relevant. But normally you'd have hundreds, maybe thousands of files, and then it has a label. This label can be anything, really text. In our case here, it's a KW for killer whale, and indicates that that segment of time in that file has a killer whale vocalization. These are the minimum fields. You could have more. For example, often you have annotations that also include frequency bounds that would have a minimum frequency and a maximum frequency. And depending on the kind of model you are using, you use that information or not. In our case here, the simplest thing we can do, we will not. So the spectrogram will be limited to 5 kilohertz. And so we are considering that anything in that range will be looked at by the neural network. So this is how it looks like. This could be created with any software you could have a CSV file, is very versatile. You could have it in XML or an Excel file. It's very easy to export to CSV. But then in order to use it with Ketos, we need to reformat things a little bit because Ketos expects things to have a certain format. But that's not too hard because we have a function that's called standardize, which basically will take that CSV file and put it in the format that it needs to be, which is very similar. If you are used to use pandas, you observe that now we have two indices here, so two levels for indexing these annotations of this table. But it's really all the same information that was in that CSV file, and you don't really have to worry about it or change it. So now we have annotations, and we know we have those audio files. What we want to do is to create samples based on that annotation that will go in that database we talked about, and then can later be used by the neural network. So I told you that we have one file, one recording that will be used for training and one for testing, and we just loaded the training annotations here. So what we are doing in this process, in this line, in this step, we are looking at these annotations that have a variety of different durations, right? You can have these were annotated close to the beginning and end of the calls themselves. So they have the duration will change from one to another. But when we are training our neural network, we would like that input to be uniform in this case. So we work with the same example we saw yesterday, which is a 5-second window. So what this line here does is exactly this. If you go to each of these annotations where we know there are full away localization, and we'll build a window of 5 seconds around it. Now, one interesting option that we can use here is that we can define a step length, and instead of having only one window surrounding that call, we can have several. We can step this 5-second window a little bit. In this case, it is 0.5 seconds at the time. And what that will give us is it will create several copies of each of the calls that we have in our training annotations, but at slightly different positions. So sometimes the call will be centered, sometimes it will be the beginning of that window and nothing else, sometimes in the end. We find that it's helpful to get the model a little bit better at picking partial calls. So, you know, sometimes when you're stepping that window through your recording, when you're actually using this model, you get like you cut the very end of the call, the very beginning. So this is helpful, and it's also a very simple form of data augmentation. This is of a very simple way of creating more training data. If we look at this table here, we see that our training set only has 260 rows, 260 individual annotated calls. It's not a lot, and in this, as I said, the purpose of this tutorial is to go to this step. In practice, you would want to have tens of thousands of samples. Data availability or the availability of annotated data is often a problem when developing these models, but yeah, you would like to have as much as possible. There are several other very sophisticated ways of doing data augmentation. Some are more risky than others, because one thing that you don't want to do is to change the nature of the signal very much. But this is a very safe form of annotation because we are not messing with the call itself. We're just changing its relative position within that clip. So when we do that, we have a very similar table to what we had before, but now all the samples have the same duration, 5 seconds, and we have a lot more. So from those 260 labeled calls, we created a little bit more than 2,600 samples for training. And that is, I mean, I should be saying training and validation, because we said that we would reserve one of those files for both. But this is the point where we would like to split these, and we want some for training, or these will go in the database as the training set that the neural network we use to adjust its millions of parameters. And then we'll have a validation set that will be used during the training to check on the model, check on how it's progressing, and give us some insight into the development process there. So what this cell is doing is basically splitting all those 2,664 rows into 2 sets. This really, it's not done. I didn't put much thought into this. I just create 2 sets. Often people will have a set proportion. So, for example, they'll take 90% of the data to training, and then 10% for validation, and they will have a different test set. Or if they have, all data together, they'll do 8% for training, 10% for validation, 10% for test. But there are all sorts of things you want to consider more carefully that we are not considering here. So one thing is so when we are talking about acoustic data, we are talking about data that's temporarily organized, right? So these samples, these annotations are not really independent from each other. So if a common practice in many other applications for deep learning is to just randomly pick samples from everywhere and then split them into training, test, and validation set. But of course, that only works if they are independent. So if we do this, we risk taking information from our test set into a training set, which would probably overestimate the performance of the model. And then when we get there to actually use it, we'll be disappointed that it doesn't perform as well as we thought it would. So these are just things that we are not thinking about here for the purpose of this tutorial, but that you would probably want to consider when creating models like this. So you saw that I've been calling these positives, and that's a terminology that is common in deep learning or in machine learning generally, especially when you are talking about a binary system. So in our case, we only have 2 possible outputs. It's either going to tell us, yeah, that's a killer whale, or no, it's not. So when it is a killer whale, we call it a positive output. When it's not, we call it a negative. So right now, we've just created the positives that we need for training and for validation. What about the test set? So we had another file reserved for test, and the process is very simple. But one thing that we probably don't want to do when creating the test is to do that augmentation thing, because then we would represent, we would just want each call to be in the test set once. Otherwise, we can have a very inflated metrics that might be a little bit hard to think about later. So this line, he just creates the selection and the clips for the test set, but it doesn't do any of the augmentation there. We don't have this stepping window. And if you look at this table, it looks very similar to what we had before. And one thing, you know, we only had 110 samples. We didn't augment it. And one thing that I'd like to just point out is that, remember, at first we had the label was called it was KW, and the Catus standard used just integers for that. So that was turned into 1. So in the end of our model, if we see something that's close to 1, it means kilowave. If we see something that's close to 0, it will be not a kilowave. And that is because right now we'll create the negative samples. So we want this model to learn to distinguish between, you know, a kilowave sample or a kilowave sound and something else. So we need to give it examples of other things that are not kilowaves. The strategy we will use here is a very simple one. So we have this file, this recording. I think this one I'm using here like 30 minutes long, and they have been annotated. So bioacousticians went through those and annotated every occurrence of the killer whales, but they also inspected the whole file. And this is important because the way we will create our negative samples is that we will go into those segments between annotations and we take samples from that. But we know that those samples don't actually have kilowave calls because that's how the annotations are produced. And that's, I think, what Oliver mentioned in his talk yesterday. One of the things that is important to document in the annotation process is that what exactly was done, how exactly were those annotations made. So if Catus can help us to do this, can go and pick random segments that are not annotated as kilowave. And in order to do this, you just need the file duration. So there's a function to get those durations for you automatically. Not a big deal if you only have one file like we have here, but if you have thousands, it's nice to do this automatically. So once you have those durations, we created the negatives in a very similar way. We create in a way that's very similar to what we did for the positives, but now we're using a different function in Catus that take it's called the random selections, which will take random places in between the annotations. These numbers here are basically just the same numbers we used for the positives, so that we will end up with the same number of positives and negatives in our database. And here's the same thing with the test. So we are telling Catus to take as many negative samples as there are positive samples. And then it looks very similar to what we had, with the difference that the labels now are 0. Well, now that we have select the negatives and positives, we will just concatenate those so they are in the same data set. So in our training set, we want both positives and negatives. And that's why the labels are important, because we still need to be able to tell them apart when they're all together. So we concatenated them, and now is the process where we take those. So far, we haven't actually touched the audio data. So we've just created this table of start and end clips that we want to take from the audio data and put in the database. But this is the step where we actually do that. And this is where we can do some of that processing we were talking about. In our case, we go into we look at each annotation that we had and each clip that we created for positives and negatives, extract that 5 seconds clip from the recording, and then we will create a spectrogram, and that spectrogram is what will go into the database, because that's what the input for the neural network will be. So that's what this step is doing here. It is loading a configuration file that tells us what kind of spectrogram we want. And these are basically the same parameters that we had in the examples we saw yesterday. I think I said 5,000 kilohertz is maximum. It's set to 6, but it will do whenever there is a conflict between things. So, for example, one of these parameters we said here is that the sample rate is 10 kilohertz. But if you're trying to create a spectrogram with the maximum we can go is 5 kilohertz then, because our signal is only 10. So that's, even if you tell it go to 6, it won't, because it can't, but it won't complain. So just 5. And okay, so we define those, and these things, you can come. This is a file that is in the computer here. Well, not in this computer, but I can't open it, unfortunately. But it's just a very simple JSON file that looks very much like this, a text file defining these parameters. And then you can go and you can change these if you want, as you want. And then with that reference, now that we have the information of what we want to do with that audio, we can actually create a database. So we do this 3 times because we have 3 different data sets, one for training, one for validation, and one for testing. And Catalyst will show the progress bar while it's doing it. And we will save these to a file. In our case, this file is called db.h5. H5 is just the standard extension for HDF5 files. And this database will be a file in your computer. If you just wanted to do that, you want to take these and use somewhere else, want to look into it, you can. But here, so once we have that database, that's what we use for training the neural network. And one of the reasons I like to put all the data that I need for training the neural network into a database is exactly because of that development cycle. Because sometimes I'll create this database, but I'll actually train the model many times because I'll be changing parameters. Or if you're actually if you're working on or something you want to publish, for example, you probably want to have some measure of variance of this performance. So you probably train, multiple models, and you will be able to measure some variance from these different models that were trained on the same data, but that due to the very stochastic nature of the learning, the optimization algorithms, it might have slightly different output. So one thing that you want to show is that, okay, if you want to demonstrate that a certain model design is a good choice for, say, creating killer wave detectors, you want to show that even if you train that model several times, you get the same results. So that's something that you want to do, and having the data in the database as opposed to doing this computation every time you need it, saves a lot of computational resource. That's the main reason why you do it. Another good reason is that you can go and you can inspect what is going into your neural network, and you can see when you test it. You can do as Val was doing and showing us yesterday. You can, if the neural network makes a mistake, you can go back and say, well, so why is this wrong? And can try to identify where the problems are. Right, so if we are doing this in this tutorial in one step, but you can do things separately. So let's say if you have that database saved, you can use it many times later in when you're training different models. If you want to compare different architectures, you can use the same input data as long as the models are compatible. So the way you do it, you use this is also part of Keras. We have a few functionalities to work with HDF5 database. But basically, what we're doing is pointing to this database and then creating a connection to the specific data set. So we have the training, the validation, the test set. And if you just look at one of these samples here, this is what it will look like this is from our test set, one of the inputs there of the kilo whale cop. I don't know which one, but once you have those the connection to the database, well, what we need to do now is create a way for the data to flow from the database to the neural network optimization algorithm. And the Keras has this class called the batch generator. And basically, a batch generator is something that will go into the database and take samples and provide those to the neural network during the training process only as needed. So one thing that might be challenging when we're working with large data sets is that you might not be able to fit all that data into your computer's memory at once. So you want to go take just the chunks that you need, and then that these batch generators orchestrate that for you. So we have that set up, and this is the step where you actually create the neural network. And it is just this one line, really. Similar to the spectrogram, we have a network recipe here, which is a JSON file with some configurations of what kind of network we want, how many layers we want, and how many classes we have. In our case, we only have 2 kiloway and not kiloway, and this kind of thing. So we create this neural network. We are calling it net. We can call anything one. And all we will need to do before we train is to just point to those batch generators we just created there. So we're saying this is the train generator, this is the validation generator. We are defining a place, a directory called checkpoints, where the network will save the current states during the training. So if you ever need to go back to one of those, or if you want to inspect and see what's going on, you have those saved. And then this line is what would actually train the neural network. And here, epochs, the number of epochs is basically how many times you want the training algorithm to go through your training data set. 100 is a good starting point, and then you can bring it down depending on what you want to do. Now, even in this, unfortunately, even in this simple tutorial on my computer, which is not very powerful, it would take a few hours to train. So what I did, I was hoping that to do more interactively, I just loaded the neural network model that we have on the Halo GitHub public for people to do. So once you train your model, during the training process, if you have a validation set, you'll be shown how the performance is progressing during training, or in other words, if and how much the model is learning what it's trying to do. In this case, distinguish between kiloweight and non-kiloweight. And then you will also have those same metrics for the validation set. So for example, this is a way I mentioned that this is a good way to catch if the model is overfitting. So if the performance on the training set starts to go up and get very high, and the validation performance starts to go down, then it's a sign of overfitting, because that model is learning the training data very well, but that's pretty much the only data it can work with. So that is helpful there. But once you have the model trained, you can save it to use later, and then we will get into that application phase that I mentioned in this slide, and then you can look into how to build a program or a software system really to take this trained model and use it for your data. So Ketos provides an API, an application programming interface for developers to use these trained models when developing new software. So if I wanted to quickly write, a program that has a web application, for example, that can, like some of the very nice web apps that we saw yesterday, that can use this trained neural network. We could do this through the Ketos API, and that would allow us to interact with this neural network and put it to use. Here is an example in just 2 lines. What you would do is, once you have the saved model, you basically load the model, and then, which we're calling trained model here, and then you would run the model on new data. So this sample here is that same sample I showed up here, the plot, where I just extracted it from the database. But in practice, this sample could be coming from anywhere. It could be coming from a live stream, and as you get data in, you compute the spectrogram, and then you have a program that will call this line on incoming clicks of data every 5 seconds, for example. Or you can write a program that will go through a whole file every hour, if that's your schedule there. But so when you run this, so what we're doing here is we're saying we're taking a sample of which is the spectrogram in that case, the one we saw there, and we are asking the train the model to process that sample. So we're running that sample through the neural network, and what happens here is it gives us an output, which is a score, 0.97 in this case, which is very close to 1, which is our target for killer whale class. If this was very close to 0, then it would be the neural network saying, I think this is not a killer whale. This is pretty sure it's a killer whale. But with these values, these raw values, or what you often do is you apply a threshold. You can apply a threshold to it, and that is often one of the parameters you want to expose in whatever application you are building around this neural network, because we saw some metrics yesterday, some plots showing metrics that show like how the recall or the precision of a model changes with this threshold. So that's very useful for when for the operation or when this model is in production and somebody is actually using it, because it allows people to adjust to the ideal place in that threshold or the trade-off between precision or the detection capabilities and recall and the false positive rates and things like that. So this is the end of this notebook and sample of code here. And yeah, so we have Justin, our AV expert here in the room. So what we want to do in front.
Do you want to do the interactive things that you plan on doing, or keeping it as a static?
Yes, I think we'll just continue like this.
Also another movie thing.
Yeah.
Do you need that to run on your computer? Would that be better?
No, it can run on yours.
Okay.
So it's already good. So I think we're good for the next half hour for the rest of the story. Yeah. Thank you, Justin. Okay, yeah. So this is a very simple example of how you could use Catalyst code to use a model, and then the idea is that a software developer could write the whole software as they do. They don't need to know anything about deep learning. They don't need to know anything about the acoustics. But if you just tell them, hey, this is the model I want you to run, and give them these lines of code, or better yet, point them to the Catalyst documentation website, which I'll show in a minute, then they can just build the software to use this neural network. Or we talked about modularity later or yesterday, and what you could do here is if we wanted to change the model, if some of you here in the room or online trained the model and said, mine is much better than yours, and I'd say, great, let me use that then. So all that you'd have to do is give me that one file, like the file we have available on GitHub, and I'd replace these with your file, and I'd be ready to run your model on my data. So I think this is one of the things we want to facilitate with Catalyst, and that's the same for other frameworks out there, is the distribution of these data. So when you train the model, how do you share it? And in this case, it is as simple as sharing a file, usually not a very large file. Well, for a regular computer, Val told us a little bit about the difficulties of running these in very small device and cabling as well. So it might be big for those times, but we're often talking about a few megabytes, 10 megabytes maybe. Can be much bigger, can be smaller, but that will be a common size. So you can just email somebody the latest model, put it on GitHub, and then people can download it and can just replace that one file, keep using their applications. So that's the idea. I will go back to my slides now, and oops, wrong slides. Zoom has this very annoying thing where it covers my, like I can't see where things are. So bring it down. Here we are. Oops.
Go on your view.
Okay, I think I'll just do that. Yeah, so we'll go I'll talk a little bit about applications, and then I'll show a few useful websites. But so basically, once we are at that point where you have a trained model, you want to build an application to use that model, or better yet, use an application that somebody else built. So this application can be as simple as complex as it needs. So it can be as simple as a simple command line tool. So this is an example of one that we wrote for our North Atlantic right whale model. So it is you go in the command line and you just say, oh, I want to run this model on this audio folder, and then you have a few parameters there. So you can say, I want this threshold, for example. This is, I want you to only count as a detection when that score we saw is above 0.7 or 0.9. You can choose what you want. And then as an output, you get a table like this with the file, the file name, the start, and in this case, the duration. So in this model, it's trained on 3-second windows. And then the score that was used here, because you set 0.7, everything that's below 0.7 won't be included in this table. But so that's very simple. We have examples of things like that on the Catalyst documentation website, which I'll show in a second. So it's very easy for anybody to come and modify or even use this one if it suits them. But and this is often how I use things, because one of the things I like about command line interfaces that it's very easy for other programs to use this program. So if I am actually intending to use these myself, and I want to say to come to the computer and type this and say, this is the file I want to run and this is the output, then this level of interaction is okay. But if I want something, for example, like vision of using live streaming data for the forecast system, we would want this to be automated, right? So we want to set a schedule, for example, and say just run this detector on the latest files that came in, every 5 minutes or every hour or anything like that. So command line tools are very useful for automated things, but they might not fit everybody's workflow or needs, or you might have people who would prefer a desktop application, a web application, a graphical interface. So one such tool is one that's familiar for many of you, PemGuard. We've been collaborating with one of the PemGuard developers, Jamie McCauley. And what Jamie did, he started as a PemGuard plugin that would be able to take one of those files with the trained neural network and run as it does a PemGuard detector. I think now in the latest versions, it is part of the core modules of PemGuard, so you don't even need to install a plugin, it comes with it. And although I don't have PemGuard in this computer here, I did get a video from Paul, who kindly recorded his use of this model on some data, and then I'll show it to you guys. Hopefully it come out well. So I can make this. Yes. Sure. Yes. Of course, yeah, I'm cool with that. I think, yeah, maybe.
This is just a short video, though, right?
Yes, and then
How much more before you finish?
maybe 10 minutes.
Okay.
I'm happy to do it.
Maybe it's a good time to break now.
Yeah.
Before this, and then do your last 10 minutes.
Yeah. And
then I'll play her report. Or just have her do it now. Have her do it now.
yeah. Okay, so for everybody online, sorry, we were just discussing some logistics here since we had a bit of a delay. We'll take a break from the tutorial now. We'll have a presentation by Emily, right? Who has been working with Orcasound. And then we'll come back to the last 10 minutes of this tutorial right after that.
Well, she's getting ready for fresh coffee.
And yeah, so just to recap, we walked through the process of training one of those models. And then we were talking about, once you have that model trained, what we do with it. And then we started talking about the possibilities of creating different software applications that we will embed that neural network and apply it to your data. And that software application really gives you a lot of flexibility to adjust the use of that trained neural network to your particular needs and scenarios. So the same model can be applied to it can be used in different software applications or software systems. So I mentioned, a very simple example and minimal application be just a command line tool that will take this model and run it through all the audio files in a given data set that we can specify. But I was about to show you a video of how to use trained models in other applications. So this command line tool I'm talking about here uses Ketos and its API for interacting with these models. But as you might remember, when I was talking about Keras, I mentioned that the deep learning framework it uses is TensorFlow, which is a very popular framework. And as it happens, the state of the deep learning is such that many of these frameworks, even some that are not as TensorFlow and PyTorch, do support exchangeable formats. So it is actually not that hard to use a model that was trained with one framework in another. So if you don't want to write code using the Keras API, or maybe you don't want to write Python code or code that interacts with Python, you can still use that exported model and in other applications. So this is exactly what Jane McCall developed in the PAMGuard project did. So James started by developing a plugin that would take the trained model and he used PAMGuard is developed using the Java programming language. And so he used the library in Java that can read the standard formats for neural networks. So he was able to import models created with Keras and more generally TensorFlow and even other frameworks. And then Jamie expanded the plugin a little bit to accommodate the other formats. So right now, if you go to PAMGuard, you have options to choose between a Keras model, a animal spot model, which is another framework for training deep learning models for acoustic, and just a base TensorFlow format. One of the advantages of using the Keras format, which and Jamie and our team were interested in was that we could add a little bit more information to that model. For example, when we were training the model, we had those configuration files, for example, that told us how to compute a spectrogram. So that goes, when you save a model, that goes in with it, and then PAMGuard, just by reading that file, knows how to process the data to pass it to the neural network. So now I'll play that video, that recording of this model being used in PAMGuard. And I'll just try to make it a little bigger. If not.
Write it on the same thing.
Hmm?
On the bar at the bottom. So it's about 33 seconds or so.
Oh, yes. Is it? No? Maybe worse. I think we'll keep it like this. All right.
Yeah.
Well, so this is a PAMGuard and using the deep learning module. So this is if you know PAMGuard, you know that it has many options, many modules, and you can set up an environment for you to use. So this is what the full setup for this demonstration. And what we have is we selected a model, so based on a file like that, like the one we produced with that code. And then on the top here is a spectrogram that is computed according to the specifications in that file. And post-selected the file we wanted to process. And at the bottom here, what we are seeing are two lines. Because the way the plugin is set up is that you have we will have one of those lines for each of the classes in our model. So in our case, we had two classes, a binary model, right? One was killer whale and another was not killer whale. So those lines will show the scores for each of those. When I was showing the code, I was showing only what we cared about, which was kilowatt, right? So when we saw that you know 0.9 score there, that was the score for the positive class. But the plugin will show both, and they are, because there are only two classes, they are mirrored, right? So what we'll see when I play is that as the audio is processed, we'll see the score in the bottom part of the screen. And what it is, what Vanguard is doing is all that process I described earlier of sliding a window through this audio file, computing the spectrogram or processing that audio file as specified by the model, and then passing that to the neural network, capturing the output of the network later, and creating a plot for us here. So,
Probably just one other question. Is there some scale to the model window in some ways? I mean, it goes up obviously when it goes up towards a detection.
yes,
It
yes,
must be constrained between 0 and 1.
yes. The plot,
Because some of the peaks are lower.
that's
It
really,
should, it should come to 1 in the binary file.
yes, that's correct. It sounds to one.
So is that a probability kind of thing then? Sort of based?
Yeah, well, it's the output of the model, the score. You see, I'm always very reluctant calling that probability. Because I think often one problem and one question with the model is that of the calibration of this output. But I think for practical purpose would be if one of those scores they're complementary, right? So it sums to one. When I showed it, I just showed the positive class,
Yeah, okay.
and the other will be just the remaining.
The reason why I was asking that, because you have that little peak there, and I look at the spectrum and there is a killer fall up there.
Yeah. So for the plotting at Vanguard, you can define the range you want to see, and it's from a little below 0, a little above 1. Because this line can go from 0 to 1, so just that you can see everything. But yeah, so 1 would mean kilowatt detected. So if we play, we'll see the model output, and yeah, we can see these scores changing when we see the localization is not it's not perfect, not very accurate in time, but it does what we wanted it to do. And I think that's the end of that file, or the end of the vocalizations in that file. So this kind of thing is like, this would be a point for us to go back into that evaluation process and see, well, it looks like those peaks, it's thinking that there is a kilowatt there. Like, is there? I don't think so, but would be worth looking into what is triggering the model, and perhaps trying to correct it with more data or more relevant samples for that. So the idea for using like a binary model is very simple to do, but sometimes it is worth creating separate classes for specific things. So even if there are things that you are not interested in, so let's say you run this model and you start to see that it gives lots of false positives for, I don't know, maybe dolphins, for example. And even if you're not necessarily interested in dolphins, that would be a good point in the development cycle to go back and say, okay, let's get some samples of dolphins so that the model can try to learn the distinction between killer whale localizations and dolphin localization and so forth. But what I wanted to do with these was basically to show different options for oops, wrong button, different options for using the trained model, right? So we can, use something like a PemGuard, which has a nice user interface and which is very widely used in the bioacoustic community. So there are lots of people who will have workflows set up with PemGuard already. So that is why we sought this collaboration with Jamie to try to get an easy way to allow those users to use these models. And similarly, the idea is that we can develop our own applications with these models. Other people can develop these applications for the same models, and those things don't need to happen at the same time. So if you are a very good software developer and have a talent for user experience and user interfaces, but you don't know anything about machine learning or bioacoustic, you can still contribute to these tools that we are using and we're talking about in this workshop. So I just have another slide that I would like to show, and that is talking about applications. I'd just like to make a little advertisement for what Meridian is doing. Oliver mentioned this yesterday, but I would just like to reiterate. And one thing is that the Catalyst package right now, it is developed as a Python package for programmers to use. So you do what I showed in the coding session, which you import the bits that you need and you write your program. But one thing that we want to add soon is to add a set of command line tools to Catalyst. So when you install the package, you already have tools such as these detection module here available to you. And if you want, you can do that whole process that we did where you write code without actually having to write Python code, just by setting those configuration files and organizing the data in the expected format. That's yet to come into Catalyst, but if you want to have a sneak peek of what will come, you can visit this repository, which is public here, and now it takes this as a separate project. But what we are working to do is to bring these scripts that are here and that will allow you to do a lot of what we covered today without having to write much code yourself. You can already look at it. And in fact, the Halo GitHub repository that contains this model that I showed today, and that's the current version of the model that we made public, has instructions for using these scripts to train models. So that is a different and easier approach to do what we did today. One of the disadvantages is that that gives you a little bit less flexibility to when you want to integrate that code into another application. But that's what we wanted to offer as another option. And the last thing I'd like to mention is that Meridian is also working on a web-based platform which we call Maple Acoustics, standing for Marine Artificial Intelligence Platform. And the idea is that we'll add different toolboxes to this platform. The first one and relevant to us is the acoustic toolbox, and you'll have several tools there for creating the data set, for training models, running the models that we did with for example, and also for annotating and validating model outputs, which is an important part of the model life cycle, right? You want to check that the model works and that still works as expected in new environments. So yeah, stay tuned, and we are developing this platform, and it will be open source as most things we do, and will be a graphical web-based platform, no coding necessary. But what you'll be able to do, you can it is designed to be very modular, so you can do everything in the platform, or you can just train the model in the platform, export it, and run it in Pandoras, for example. And yeah, so that is to come. Yes, so this is all that we wanted to share today for the tutorial. Appreciate the patience, everyone, especially those online. We did have quite a few glitches, but I hope this was somehow insightful for you, and feel free to send me an email. I think everybody has my email, and we will share the slides and the recordings and all the material soon, along with all the rest of the material for this conference. Thank you very much.